Everything's sticking there, right? You'll see the screen? All right. It'll stick in here a little bit. All right, nice. So lastly, most important thing, we spend some time on logic gates, right? I didn't save that. So you spend some time on logic gates. You want to continue with logic gates, right? And we want to move on to some other applications. Lastly, we did a binary addition. So as a revision, just do a quick addition for me. I'm giving you a 3-bit. What I want you to do with the 3-bit, add it and do a added chip for me. Not the circuit, the block diagram. Do a block diagram that will work for that added chip. A block diagram that will work for that added chip, right? All right, let's see how the other chip went. We had a chip. So 1 0 is 1, 0 0 is 0, 1 1 is 0, carry 1. Correct? And how much things do we need for the other chip? We need, right? Correct. We need 3 things for the other chip. We need a half adder here. And we need two full adders. Why is the first half adder? Because it only has 2 inputs. So so technically you can say 2 half adders, but remember 1 plus 0 is 0, carry 1. Sorry, is 1 going here and it carrying a 0. So technically there's a 0 on top there, right? That's why I need a full adder. And here we're carrying a 0 again, right? So you still need full adders. So you have a half, like my pen there, right? So you need a half, and 2 full. So you need a half adder, a full adder, and a full adder, right? 2 inputs go in here, you have some, carry. 2 inputs go in here, you have some, carry. 2 inputs go in here, we have some, carry. Okay, so that will be, here's 1 0, here's 0 0, here is 1 1. Right? So here we have 1 0 was 1 carry 0. This is 0 0 here, and this was 0 1. Oh, yes, read it. Remember, most significant to least significant. Okay. All right. So that's what we did last day. We spent some time on the other chip, and I think I asked you to use the do a circuit diagram. So you have to do that. Right? Put in the circuit diagram for the half adder and the full adder and connect them up. All right. So I want you to do it. It's just wait to see it. Right? All the questions that I've seen on this, they have the block diagram. But I want you to still put together the circuit diagram. Okay? You did the one for the full adder? Circuit diagram. Yeah, man, nice. Well, I'll have to do that one, right? So I will do it. Anybody do it online? The circuit diagram for the full adder. Come on now, one person give us some hope now, please. Just one person. Right? Remember, we had a which one I'll put on top again? The exclusive or the AND gate? Which one I'll put on top for the half adder? Circuit diagram. The XO on top? Okay, all right. Okay, so that was your I1, I2. This was your sum, and this is your carry. Right, so for your full adder, your block diagram would have been 2 half adders and an OR gate. 2 inputs go in here, I1 and I2. Sum go in here, previous carry go in here. That's like your I3. 1 carry go in here, 1 carry go in here. And this is your final sum, this is your final carry. That was the block diagram. I wanted you to take this diagram, put it in here, and connect it up. So I don't want to see the block diagram, I want to see the circuit diagram alone. Do that for me, please. So take off the half adders and put the circuit diagram. Right, so it's ready for you to just connect it up. Just put the appropriate connections and you're good to go. I'll do it just now. Yep, correct, Shivani. So if they ask you to draw the circuit diagram, that's what they want, right? Every time. Okay, so those are the connections that you'll make. So if you have to build a half adder circuit, that's what you'll do. You'll use those gates and build it. Sorry, a full adder circuit. You're looking with that online? Nice. Copy it down. And well, that's a full adder there, right? Let's move on. There's something called control circuits, right? I just want to show you. Control circuits is what you would have done like in Form 5. I don't know if you remember the example with the kettle and you're using gates. And at a certain temperature, the kettle cut off using simple logic gates. Well, anyway, you could use simple logic gates to control actual real life devices, right? I want to show you an example. Hello? Yeah, so with so just yeah, that's it. That's it. Current going there? Oh, that's on this side to current 20. Right. So we're looking at real life application. So for example, I just giving you as an example, right? You can use a NOT gate as a switch to turn something on and off, right? So you have some circuits that you could use to control a lot of things, right? Just give me 1 second. Let me see if I can find this back. Happens I'm not seeing the original. Don't know where my original handout is. That place always so good I can't find it. But I know I have it here. Right, just give me 1 second to online. Actually, it might take more than one. Right, see, I'll start over. Ba, 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 ba. Urban. You're not gonna attend though. It's just Saturday, just one day. Well, yeah, Friday is no weekend. Well, yeah, Friday and Saturday. Why, what happened? Yes, but yes. Even if I put it private altogether. But I wouldn't put, it will be open. Why, you're going cricket or? Yeah, lie, you're going cricket, and I remember I said cricket in the oval. I feel like going cricket. Last thing, if I don't get it here, I'm gonna know. No, I have it. I just can't remember what I saved it as. Somewhere here. Da, 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 da. All right, so good. Here we have a scenario. We have an AND gate and an OR gate. And we have 3 people, A, B, and C. Adams, Bahanji, and Miss Clark. And you have to figure out, well, you have to complete the circuit. When you complete the circuit, you have to figure out who's the boss. Right? So here's an example of using 2 gates as a lock. It's an electronic lock. Right? There's one person in particular who has to be there. Of course, he or she is the boss. So draw the circuit, do the truth table, and let's see if we can figure out who's the boss. Right? The heading is control circuits. Right? The heading is control circuits. Right? Online, who's the boss? Who Clark? You'll have some of you all have Clark. Who's the boss online? Right, I have a few C's so far. Anybody else? Who again? C? C? What do you got? C? All right, let's see. Looking like it's C. So let's see if it's C. Yeah, C. All right. Let's see. D as an AND gate, right? So that would be 0, 0, 0, 0, 0, 0, 1, 1. As an AND gate, right? OR gate for E, you're looking at D and C. So that's 0, 1, 0, 1, 0, 1, 1, 1. Right? So it'll be open. It'll be open here, 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 and here. If all three of them there, it will open. So that makes sense. But here is the only case where it have one person and it open. So in that case, that one person must be the boss. She has to be there. Clacky has to be there to get it. Okay. So here's an example again of control circuits. One more control circuit. Right. Any questions there online? Rika? Benicia, any questions? Wait, what everybody else? Any questions? All okay? One more. Try this one here. This one though, you have to design the circuit. They're just showing you how to set up the truth table. So you have a spring-loaded switches in the door of two cars come on when it owns a logic 1, when the door is open. So when the door is open, it's a logic 1. If the key is in the ignition, it's a logic 1. A door is not closed properly, a red warning light comes on. So if you have the key in the ignition and one of the doors open, a red light comes on. Right? Draw up a truth table for this system and then design a suitable circuit. So the reason that you have 3 inputs here is because you have 2 doors and an ignition. Right? You have to write out what the output should be. And then from that, you work backwards using an AND gate and a AND gate and a AND gate and an OR gate to figure out what the circuit will look like. So you have to design the circuit. In the last question, they gave you this circuit. And this question, you have to figure the circuit out. Okay? Read the information, do the truth table first, and then see if the circuit that you create works out. They kind of give you a hint and tell you what 2 gates to use. You just have to figure out how to connect it. How to connect it. If you read the information over, it kind of give you an idea which inputs go into which gates. Take a 2 minutes and read the info.
Yes. So there'll be English and then either the one or the so it is for English or not, right? Then English and the rest of them. But if you want to both doors are closed, so that one will be as well. The last year, each one of them has their own. So that would it be or and or which would bring okay,
Right, so you had to figure out the gate, right? But how should it work? Put anybody join it online, you can send it from her, right? So if everything off, nothing should come on, right? So this should be 0. If the ignition not on, that should be 0. So first 4 is 0. If the ignition on and the doors it'll be 0. If one door open or if 2 doors open. So you have 3 ones on the end, right? Good. Now you have to figure out where the OR gate going and the AND gate going, and then connect it up. Only 2 gates, yeah, only 2 gates, yeah. Right? So the circuit requires an AND gate and an OR gate. That's all. If you think you figure it out online, someone pick up it. Katrina Sandhills and Celine, let me check it out. Katrina, that looks correct. Celine, that looks correct. Right, just draw the output connected to the alarm, right? Well, no, not the alarm, the red warning light. I have it. So all you have to do is figure out what going to the OR gate. What going to the OR gate? Huh? It does? It does. So that's all you're doing. You're joining a gate here and you're joining 2 doors. D1 and D2. Where the ignition going? To what? the ignition going to the red while a closed state. So, but and the gate have to be there too. No, and say AND gate. What's the next input for the AND gate? Yes. That's it there. And then going to the red light. That's it there. That's what you do. So normally what you do is do the truth table first, write out what the output's supposed to be, and then from that you normally figure out what gates you could use. Okay. Copy down. Let's take a look at one last thing. Da, 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 da. And last one here. Oh, wait, no, same thing. All right, no way. I thought I had the past paper here, but I'll have to go and look for it. All right. So the next thing that we're going to look at, sorry. The next thing that we're going to look at is the next application. This is called the bistable. It's called the flip-flop. Or the bistable. Right? It could be made using the AND gate, sorry, the NAND gate or the NOR gate. I am going to show you the NOR version. Right? What's the summary for the NOR again, Olia? What's the summary for the NOR? Something always give you something. I'll give you one piece of homework to revise this. A 1 gives you a 0. Right? So a 1 will always give you a 0. So it don't matter what the next input is. Once you have a 1, you'll always get a 0. Right? That's a NOR gate. Right. So we're going to draw something called a flip-flop or bistable. These gates were used to save information long ago. So like if you want to remember all the information that computers ones and zeros. So if you want to save a 1 and then reset and save something else, you used to use a flip-flop long ago. All right. It's like a kind of the components that make up a whole hard drive. So you're taking 2 NOR gates. And you're connecting them up like this. You have I1 here, that's your first input, your second input. You have an output, one is Q and one is the opposite of Q, so you call it Q hat. The output from Q becomes the input for the second NOR gate. The output from here becomes the input here. All right. So I want to show you how it will work, right? All right, join us now. Watch it here. Let's see how it works. So our first 2 inputs are 1 and 0, right? 1 enter NOR gate gives you a what? A 0. So you will recognize that initially that there is none of them have 2 inputs. You'll see enough? None of them have 2 inputs. So, but you don't need that, right? Because a 1 will always give you a 0. And then that output is fed back into the input of the second NOR gate. So that output will come back all the way here. You'll get 0. 0, 0 will give you 1. 0, 0 in a NOR gate will give you 1. That 1 will come all the way back up here. 1, 1 will still give you 0. So the first set of outputs are 0 and 1. That's okay? And the reason it's called stable, because the only way this flip-flop functions properly is if Q and Q hat are opposites. In this case, you see them being opposites. So that's said to be same. Sorry, that's the first set of values. And it's called a stable state. Okay, so 1, 0 give you your first stable state. If any input give you 2 1s or 2 0s, that is not stable. Okay, that will make the flip-flop go crazy and it won't work. All right. So now look at what we're going to do. I'm going to change the input from 1 0 to 0 0. Let's see what will happen. So I am going to change the 1 here to 0. Right? Now let's look at it. 0 1 into a NOR gate gives you what? The first NOR gate is the first and the second, right? 0 0 1 into a NOR gate gives you no change there, right? No change there, no change here. 0 0 into a NOR gate gives you what? 1, no change here. That's okay? 1 fed back here, 1 0 still giving you 0. So what you recognize? There's no change. So this step here, by converting a 1 to a 0, is called save. Or some books, some past papers call it latch. Right? So you just save 0 1. That's okay? That's it. That's the way it works, right? That's save. Now let's flip it now. Let's see if we can save something else. So I'm going to try to write now in green. Here's what I'm going to do, right? Taking off. I'm going to take off. I'm going to turn I1 to keep I1 as 0, but I'm going to change I2 to 1. Let's see what will happen. 1 will always give you a 0. 0 going back up here to give you 0. 0 0 will give you 1. 1 come back down here and one come back down here. So you get 1 here. 1 1 will still give you 0. So what happened to your output now? Your output is now, right? That's okay. So by changing this, you kind of flip the output. So sometimes it's called a flip-flop. Okay. And then what do you think 0 0 will do? If I change I2 to 0, what will I do? Yeah, you can do that mentally. So what happen? So you'll get back 1 0. So you save it again. That's okay. So by flipping the inputs, you're resetting it, right? That's why our next name is RS flip-flop. You're resetting it, and then by putting 0 0, you're saving it. Okay. That is your NOR flip-flop. NOR flip-flop. Copy it down. Oh, what about 1 1? Okay, that's a good question. I'll put it in red. What about 1 1? So if I put 2 1s here, a 1 will always give you a what? A 1 will always give you a 0. A 0 will come back here. 1 0 is till 0 come back here. What happened to the Q and Q hat? They are the same. So this is a disallowed state. Right? And the reason it's called bistable is because you only have two stable states. Those two. 0, 0 is considered to be safe or latch. That's okay? So you don't want the disallowed states. Copy it down. There's no flip-flop, right? Ba-da-da-da-da-da. Ready? Let's take a small note. The bistable of flip-flop. That's a smaller thing. The bistable of flip-flop can be constructed. The bistable of flip-flop can be constructed using NOR or NAND gates. Using NOR or NAND gates. Full stop. It has two stable states. It has two stable states. And can be used to save or latch onto data. And can be used to save or latch onto data. Full stop. For the for the circuit to be stable, both outputs must have separate, for the circuit to be stable, both outputs Q and Q hat must be opposites. Both outputs Q and Q hat must be opposites. Full stop. Above is the NOR flip-flop. Above is the NOR flip-flop. And below is the NAND flip-flop. Go ahead. I want you to do the NAND flip-flop for me now. Same thing. You're doing the same thing. I'll just set up the truth table for you. I want you to do the same thing for the NAND. Just change out the NOR and put a NAND. And I want you to do it for these outputs. See if we can complete this truth table for the NAND. Right, try to complete the truth table. What's the summary for the NAND again? 0 gives a 1. I try to complete the truth table. Again, you don't need two inputs, a 0 will always give you a 1. I do it with any circuit and pencil and say, put your 1 and 0 again. Okay, 1 and 0. Start over. 0 always gives our 1 going. This one coming back. Okay. 1 giving up. Right, so let's do what 0 coming back is out. 0 1 right there, the 0. So it's 0 1. Anybody see any use for a circuit like this? Why you can use a circuit like this for? A practical use. What could be a practical use for a circuit like this? You'll finish this circuit there, Raul. Karina, you'll finish this circuit. Let's see if your truth table correct now. Finish? I'm almost okay. I'll give you 2 minutes. In the meantime, try to see if you can figure out when we will do something like that. Besides in a computer to see. When again you might need something like this. When again a circuit like this could be useful. Come on, I finish her. Raul, I will start to do it, right? Renel, you got you? Yeah, okay. Let's try it now. All right, so I'll do it here in blue for you. So I1 is 1, here is 0. In a NAND gate, 0 always gives you 1. So there's 1. 1 coming back here, 1 will give you 0. 0 fed back here is 0. So you get in 0 1. Is that stable? Yes. 1 1 now. Let's take off this here and put 1 1. 1 0 into a NAND gate, still giving you 1. The 1 going back up, 1 1 still giving you 0. 0 coming back down. So therefore, what do we do here? We save our latch, right? That's okay? We end up saving there. Now, Let's take off the one on top and put 0. Only that, only I want it. 0, 1 will give you 1. 1 in Q is now 1, so when you rub off here, this has to be 1. 1, 1 entire NAND gate is 1, 1 entire NAND gate is 0. So you basically flip the output to 1, 0. Okay? What will 1, 1 do? 1, 1 will save. Okay? Let's change both to 0 now. 0, 0. 0 always give you a 1. So you have 1 there, you have 1 here. 1, 0 will give you a 1. 1 come back down. Slight problem. We end up with 2 1s. So this is a disallowed state. Okay? So you have both flip-flops there, the NAND flip-flop and the NOR flip-flop. All you have to do is just remember, besides how to connect them, you have to remember the summary. And that's it. You can figure everything else out. Right? You'll recognize that 1, 1 is the save for NAND, 0, 0 is the save for NOR. Okay? All right. Follow up 10 minutes. Right? One application of this is a burglar alarm. So a burglar opens the door, and when you open the door, you try to close it back because here the alarm went off. Although we close it back, the alarm's still going off because it's saved. Right? And well, hopefully they catch him. All right? So take a little 10-minute break, and then we are going to take a look at our application of this. Okay? Take a little break. Yeah. Oh, I'm collecting something. Oh, why doing it now? Yeah, the school open. Oh. When school open, I might see them teachers come out with bags and bottles. Right, yeah, try this one. Sorry about the quick, but as the press said, you don't have to draw the circuit, just come to the table and answer the questions. You gotta recognize one time what it is, right? A flip flop, right? No flip flop. Right, so we have a burglar there. We have a burglar. Let's see if we could. Let's see if we can work it out. Fill out the truth table and answer the next two parts. Wait, did I unmute? Right. There you go. There you go. The handle that's supposed to give you all this handle, but I don't know where it is. There's a handle with the whole module. Somebody else scan it and keep it, but check back her email and again. Right in front of that one. I have tried. The little line saying I gotta put some words, right? Right? They didn't give a Q and Q after just give a Q over. Right? You want to be comfortable if you Q out on the
Yeah, yeah. You're also going to be on your. It's there. No, I just think like, I'm only to, I think feel like class, I'm going to be done about this. I have. Yeah, around some.
All right, let's check it out. Let's go again. It worked out, hopefully. All right, let's see. So let's see what happened to the burglar here. So the circuit below shows a single alarm designated, sorry, designed. Oh, watching the wrong one, right? Right, designed to sound when a burglar attempts to open a window of a small shop. To prepare the alarm, the owner closes the window and uses the push button to operate push button operating switch to briefly connect I1 to 6. 6 is like high, right? It's like a 1, right? And the earth symbol here, that's the earth symbol, is like 0. Right? Then return it to logic 0. Right? So the switch is what you're using to go from 1 to 0. So this is shown in lines 1 and 2. So in line 1, I1 is a 1, then he turn it to a 0. By doing that, he allow Q to be 0. He save it, right? So right now the alarm is off. But now the burglar tried to, so when the owner closes the window, I2 is set to logic 0. If the burglar attempts to open the window, then I2 is a 1. Right? So when I2 is a 1, here's a 1. We know that a 1 will always give you a 0. So a 0 will come here, 0 will come here, and this was 0, 0, 0 is 1. So it appears that Q will go off. Okay? So Q will become 1. So the question says to complete line 3 and 4 and see what happens when the burglar starts to open the window, then rush to close it. So when the burglar closes back the window, I2 goes to 0. But we know that 0, 0 will save. So it will save the input and output on top. So you'll get 2 1s. That's okay? So the alarm will sound here and the alarm will sound here. So what you have to say is the alarm sounds, right? And when the burglar tries to push back in the window, the alarm stays on. Okay? So the alarm doesn't go off. So although we push in the door and this became 0, the alarm is still on because Q still stays 1. Right? How to switch off the alarm? What to do? Huh? Press the button. You switch. So you have to turn the switch on and off again. So you have to switch back the switch here to 1, 0. And then this will happen. Here will become 0. And then take off the switch and the switch I1 will go to 0. So you have to do the flip. You have to turn I1 to 1 and I2, send I2 back to 0. Right? So you have to do what he did here to prepare it. Okay? So by pressing the switch, converting I1 to a 1, and then releasing it and turning it back to 0. Okay? All right. I just going it over. Selena will confuse it. Are you okay with it?
Yeah.
All right, so let's go. So the owner closes the window and pushes the button. So when he closes the window, it becomes 0 and he pushes the button 0. right? So what I will do is that I will save the Q to 0. Then the burglar tries to come in now through I2, and I2 will now become a 1. When I2 becomes a 1, we know 1 will always give you 0, 0 come back here, and you'll get Q to be a 1, right? Now, if the burglar tries to close back the window, he turns in the 1 to 0. But I wouldn't do anything because all I will do is just save the previous output, right? So the alarm will sound here. The alarm will stay on. To take off the alarm now, the owner has to press the button, right, which will turn it back, which will turn back this window, but he kind of has to open the window too. Open the window and press the button. What I will do is that will turn this one, turn I1 to a 1, I2 to a 0, right? And the alarm goes off. And then he releases the button. I1 will go to 0 and this will stay 0 and stays off. That's okay? So to take it off, you have to press the button. Celine? You okay there? So line 1 and 2 is the set, line 1, 2, 5, and 6 is to set the alarm. And line 3 and 4 is where the burglar tried to open and close. Okay? All right. So that is your flip-flop. There's one just like it's in the past papers, but I think it's a NAND. Huh? You all wrote down the worded part? Write down the worded part, eh? What they asked for, the alarm sound and all right, let's squeeze in one more, and then we have one last thing to do in digital. Leave it there. Let's take it off. Taking it off, right? This is 2011. This is 2011 of the camera. Oh yeah, the camera now working. Don't know why this happened. Every time zoom on, that's something. Right, this is 2011 here sending you. Last one. So we connecting it up and doing the truth table. Should be easy.
That's what. Of that, yeah, is about 55. Each drug, it's a good. No, well, one of them will be a foot, they have to index, and one will be upper. Yeah, that's what I'm saying. It's one of them. It's the house. It's the yes. There's also. That's all. Yeah, they were sure of it. Yeah. Old cup, though. Okay, okay, okay. Yeah, okay. You just look very deep. Yeah. Yes. No. Oh, I already know that. Did you go to see that? No, I don't. I don't. What's your terminal digital? Okay, see that.
All right, nice. Now we connect it up here and then finish with that, right? right? So they ask you to collect, to show that, use it to do a RS flip-flop. So this go in here, this go in here. That's it. You don't need these, right? Plenty people got it wrong in that year because they thought they had to use all four, right? But remember I told you earlier that although you have a quad node chip, you don't need all four. You just connect what you need. Okay? Lots of people got it wrong because of that. And last thing, a friend asks you to demonstrate, how this circuit acts as an electronic latch, perhaps as part of a burglar alarm. Complete the sequential table on the right hand and use it to assist, right? And we know this already. 0, 1 will give you what? 1, 0, right? 0, 0 will save it. 1, 0 will flip it. 0, 0 will save it. 1, 0 will keep it the same. And 0, 1. Because they didn't flip. Right? So you leave it as slide out. Okay. So here you save, here you save. Thing is, they didn't change anything. Right? This is the same output as this. So these two supposed to have the same output. That's okay? Okay, nice. So that is it for flip-flops. Right? There's a NAND flip-flop somewhere, but I can't remember what year it is. But there is a NAND flip-flop somewhere. Right? Last thing we have to do, this task is 3 or half 3? Half 3. Right, we are 10. Nice. Last thing we have to do is a T-type, something that's called triggered. Right? So based on the input, it will trigger the output to change. All right. Okay, so this here is your triggered by table. Okay, so what will happen here is that there's a consistent pulse that keep coming in. So it's like you're taking this and you're going up and down. So it moving here, then and so on, right? So the input is 0, then to 1, then back to 0 and so on. Right? And what you have is a trigger. We have different triggers. The trigger in the example you're seeing is a downward pulse. So the trigger here is a downward pulse. So basically it means when a 1 becomes a 0, it will trigger the output to change. Okay? Let me show you how it works. Right? So watch this here. Right? So watch this here, right? You have a 0, right? Going to a 1. Because your output starts at 0, it's going to stay 0. That's okay? So a 0 going to a 1, it's not going to tell the output anything. The output will stay the same. So the output will stay 0. Right? But the next pulse, which is a 1 going to a 0, tells the output based on the trigger, it will trigger the output to change from 0 to 1. Say enough? So it triggers the output from a 0 to a 1 to change. So it went from a 0 to a 1. Right? Now you have a 0 going to a 1 in your input. That will not do the output anything, so it stays the same. 1. You'll see enough? Now there's a downward pulse again. So when the downward pulse comes in, that's a trigger. So it will trigger the output to go from 1 to 0. Right? 0 to 1, not a trigger, so it stays 0. 1 to 0, trigger. So it will change. 0 to 1, not a trigger, so it will stay the same. The output, that is. 1 to 0, that's a trigger. So your output looks like that. And that's the way the T-type works. The trigger is not always a downward, it could be an upward pulse. The question will tell you. So based on the input, it will trigger the output to change. Are you okay with that? Shabara, you sure? All right, so I'm going to show you one more time without this. That's the input, right? I'm using the same trigger. 1 to 0 will trigger the output to change. So the output now, the output starts at 0. Right, look at the input. When the input goes from 0 to 1, that is not a trigger, right? Remember, this is your trigger. 0 to 1 will not trigger the output to change, so the output will stay 0. 1 to 0, that's a trigger. So it tells the output that it has to change from 0 to 1. Okay? Look at the input now. The input going 0 to 1. That's not a trigger, so it stays 1. 1 to 0, trigger it, goes to 0. Okay? Stays 0, then trigger to 1. That's okay. You'll see a pattern here. Every 2, it will change. See that? Okay. So that's a T-type. Head up T-type bistable. T-type bistable. Right, small note, a T-type bistable. A T-type bistable is one that is triggered, to change its output. Is one that is triggered to change its output. Is one that is triggered to change its output. Full stop. Full stop. When the trigger is met, for example, a downward pulse, when the trigger is met, for example, a downward pulse, the output is forced to change. The output is forced to change. Otherwise, the output remains the same. Otherwise, the output remains the same. Otherwise, the output remains the same. Full stop. Right? And draw the blocks, draw the diagram, draw this diagram and the output. Right, remember I told you the trigger is now always the same, right? Triggers will vary. All right, so this is one, right? Suppose we connect one to the next. Suppose we connect one T type to next T type to next T type. What do you think might happen? What y'all think will happen? Any ideas? All right, I'm tired. All right, let me show you what will happen. Oh wait, I don't have it. All right, I think this is here, right? Well, let me draw looking better here. Suppose I had one, right? Same trigger, downward pulse. You all see that the output from Q, the first Q1, becomes the input into the black one there, Q2. You all see that? The output from Q1 is now the input for Q2. You're seeing that, right? So watch this here. See if this diagram make any sense. You should understand Q1. Every downward pulse causes a trigger, right? Andy, you can explain Q2 for me? Say that again. Every upward pulse will be the trigger. But remember, this is the input to give it Q2. You sure it's an upward pulse triggering it? No. What triggering it? Downward. Don't quiet, but don't. Right? So yes, a downward pulse. So look at when it went from 1 to 0. It triggered 0. The trigger was 0 to 1. See that? See how it switch? Look here again. Next downward pulse. Downward pulse. The output trigger from 1 to 0. Okay. See pattern now? Every how long does it take to change? 4, right? So the first one, it take 1s, here it take 2s, here it take 4s. I make a guess. How long will it take in the third case? So suppose I connect one more. 8. So that sounds like, well, that's binary, the base 2. Remember that? So technically what you creating here is a counter. You're creating a counter here. You're creating something that can do counting for you. 0, 1, 2, 3, and so on. All right. I don't know what you're gonna do. You can take a picture or you can draw it. And your homework is to do 3. All right, so here what to do. You can take a picture, I don't mind, but your homework is to do 3. 3 Q1, Q2, Q3. So I want one diagram with all 3 in it. Okay. So I don't mind if you take a picture for this one, but I want one diagram that will move on here to Q3. And you will have 1. You will have 1, 2, 3, and 1 more 4. Okay. And do the lines here, right? So you can screenshot this one, but I would like to see for homework 1 with 4. If you don't do it, well, we'll just start Saturday class for now. All right.